Okay, lecture number 9. And today we will discuss face portraits. Face portraits of plane differential equations. Well, although it is usually very difficult or impossible to obtain explicit solution of a differential equation, it is very important to make a qualitative analysis of an ordinary differential equation, and to a considerable extent this can be done by using phase diagrams. And today we will speak about phase diagrams, and we start with the definition. Today we will speak about autonomous differential equations. So an autonomous differential equation is an equation of the form x prime equals f of x. So here you can see that the function f doesn't depend on t, on time. Okay, so f from Rn to Rn, so not from Rn, so let it be from D, from some open set. Suppose f is defined on some open set D. D is some open set and f is a continuous function on D. Okay. So autonomous differential equation means that f doesn't depend on t. F depends only on x. And in this case, we can consider phase diagrams. So D is called a phase space. Phase space. And we will consider orbits or phase trajectories in D. So today we will not speak about integral curves. Integral curves and phase trajectories are different things. Okay, today we will speak about phase trajectories. This means the following. So if x of t is a solution, so let it be a definition. This is a definition. If x of t is a solution of equation 1, is a solution of equation 1 with maximal interval I. So the notion of a maximal interval was discussed in the preceding lectures. So I'd like to recall some facts about maximal interval. So by Picard-Lindelöf theorem, if by Picard-Lindelöf theorem the solution exists and unique in some open interval of the initial point, and the solution can be extended in a unique way to some maximal interval. So if x of t is a solution of this equation with a maximal interval I, then the set x of t, the set of points, it is in D, is called an orbit or phase trajectory. Phase trajectory. Okay, now let's discuss the difference between integral curves and phase trajectories. So, integral curves. Okay, please turn the camera to this wall. Well, so integral curves and phase trajectory or orbit. What is the difference between them? So both are related to a solution of a differential equation. But for the integral curve, we need the graph of the function t, x of t. It is in Rn plus 1, in dimension n plus 1. But the phase trajectory is just the projection of an integral curve. So the set of points x of t, t is in I, and it is in Rn. Just so the phase trajectory can be considered as the projection of an integral curve to space Rn, and sometimes it is more convenient to analyze phase trajectories or phase diagrams, so a phase portrait or a phase diagram. Oh, hello. So a phase portrait or phase diagram is the representative set of phase trajectories. Okay, well, now we'll make a figure. Okay, suppose we have, so now we are in R3. So this is time, and these are x and y axis, x and y axis. And suppose the integral curve, so this is the plane in R3. Suppose we have something like, so I speak about an integral curve. So suppose we have something like a spiral. So this is an integral curve. And what about a phase trajectory? So a phase trajectory is a projection of an integral curve to a phase space. So this is a phase space. It is two-dimensional. Well, maybe I will recall something. Okay, for you follow. Well, so now we can see the autonomous differential equations of the form x prime equals f of x, where the function doesn't depend on time, on t. They are called autonomous differential equations. Okay, so D is the domain of the function f. F is continuous in D, and it is called a phase space. D is a phase space. And this is in this definition, I define an orbit of phase trajectory, which is the same. So these are two same things: orbit or phase trajectory. And I'm trying to compare the notion of an integral curve, which was studied before, and the notion of a phase trajectory. So an integral curve versus phase trajectory. So, and the fact is the integral curve is a projection. The phase trajectory is a projection of an integral curve. So I will make a picture using the colored chalk. So it will be something like this. So if we have a 3D spiral, we can consider a projection of this spiral. So this is an integral curve. This is the direction of motion. And the projection of an integral curve will give us a phase trajectory, okay, with this direction. Okay. On plane, in plane, right? So it is in space, in 3 space, but phase trajectory in plane, right? Because the dimension for phase trajectory is of space is 1 unit less, right, than for integral curves. And sometimes it is more convenient to study phase trajectories because our space is 3-dimensional, right? And it is more convenient to sketch some figures in plane than in space, right? It is more convenient for a person, for people, and so a lot of information about autonomous differential equations can be obtained from phase portrait, from phase trajectories, and a set of phase trajectories, a representative set of phase trajectories. So usually we draw several space trajectories, and this set represents a phase portrait or phase diagram. Phase portrait is a set of phase trajectories. Well, phase portrait, phase diagram. Now we will prove a theorem which states that the integral curves are invariant with respect to translation along t-axis. Well, so the trajectory. So I will use this space. It will be theorem 1. Let it be theorem number 1. Okay, so let x1 of t be a solution of the equation x prime equals f of x, initial value problem, x of 0 equals x0. Then x2 of t, which is equal to x1 of t minus t0, solves x prime, solves this equation. X of t0 equals x0. So if we compare these two equations, we can see that so the equations are the same, and initial values, so x0 is the same here, but the starting time, the beginning of our motion is different. So we start with t equals 0 here and with t0 here. So this is the translation of t-axis. But this theorem shows that if we want to solve this equation rather than this, the first one, we must make the translation in t-axis in the solution. So the functions are the same. This is just the translation in the argument, but the phase trajectories will be the same, right? The phase trajectories will be the same because both phase diagrams are projections of integral curves, and both integral curves will be mapped into, will be projected to the same curve, Well, let's prove this. Well, if we make a change of variables, a change of time, let us introduce new variable s, which is equal to t minus t0. Then we can see that ds equals dt. Suppose x1 of t is a solution of this system, of this initial value problem. Then let's consider the function x2 given before, given by this formula. It is x1 of t minus t0. And I want to show that this function satisfies equation number 2. So let it be equation number 2, and this is 3. So because number 1 belongs to the first equation, the initial equation, right? Let's differentiate. So d over dt of x2 of t is equal to d over dt of x1 of t minus t0. So I have substituted, so by definition, x2 of t is the same as x1 of t minus t0. Then let's make a change of variable. Since ds equals dt, then it is equal to d over ds x1 of s. As x1 solves this equation, it means that it is equal to, so the derivative is equal to f of x1 of s. But it is f of x2 of t minus t0, x1. It is equal to f of x2 of t. So proved. I have started with this, and I have ended up with this. So if we compare the beginning of this row and then the end of this row, we can see that the function x2 satisfies this equation. This is the first step. And next, we need to check that x2 satisfies this initial condition. Let's find x2 of t0. By definition, it is equal to x1, so this is the definition of the function x2. It is the same as x1 of t0 minus t0. So it is x1 of 0, and it is equal to x0. So we have shown that x2 satisfies this initial condition. So theorem is proved. Well, Now, so I will use that part of the board. In what follows, we will need the notion of a critical point or equilibrium point. Okay, the solution of the equation. So a solution maybe. So there may be several solutions. A solution of the equation f of x equals 0 is called an equilibrium point or equilibrium solution or a critical point. So f or critical point. So and let it be lemma. If x0 is a critical point, then it is an orbit, so it is an orbit or a phase trajectory. So an orbit, just a point. A point can be an orbit. So in this or phase trajectory. Well, because so if we consider function x, which is identically x0, doesn't depend on t, and if we differentiate this, we will get 0, right? So then, if we differentiate this function, this is a vector function, all the components of this vector function do not depend on t, and if we differentiate, we will get 0. But it is equal to f of x0, because x0 is the solution of this equation. Let it be x0. So we can see that if x0 satisfies this equation, then a point is an orbit, right? A critical point or an orbit in phase space. But what about the integral curve? Is the integral curve a point or a line, or what is the integral curve of this solution? Just straight line, right? And the projection will be a point. So in R3, for example, if I have something x, y, and t, so the projection to this plane of this straight line, so all the components are constant, they do not depend on t. So this is an integral curve, but that projection will be a point, just a point. Well, and now let's look at the example. At an example, I will use this part of the blackboard. Okay, an example will be So familiar for us, x prime equals x squared. So the right-hand part doesn't depend on t. And in this case, we can consider an integral curves, and phase trajectories. So integral curves will be in R2, right? So this is one-dimensional. So we can see integral curves in t-x-axis, so x versus t. So this is for integral curves, and so this is t, this is x, and the projections of integral curves onto x-axis will give us phase trajectories. So let's solve this equation. The variables are separated. It will be minus 1 over x equals t plus c, and x equals minus 1 over t plus c. And we have lost the trivial solution, x, which is identically 0. So if we divide by x, we should consider this case separately, and this is a solution, x, which is identically 0, and these integral curves, right? So this is our first. So this integral curve is this straight line. And what about these integral curves? Minus 1 over t plus c. It is something like these integral curves. With asymptotes. And we continue for negative. Well, so we have studied, we have already considered this example. And we know the maximal intervals for each of these solutions. So the maximal interval will be from negative infinity to negative c, and from c to positive infinity. And just a point. These are maximal intervals. So what about, so these are integral curves as before, but what about phase portraits? So we should consider projections of these integral curves. If we consider projections, we will get the following. So our phase space will be one-dimensional, just this axis, right? So the dimension is minus 1. We will see a point. This is a critical point, or an equilibrium point, right? Equilibrium point. And two rays, right, r plus. The projection of these integral curves will give us this ray. And projections of these integral curves will give us this ray. Okay, what are the directions of motion? So the direction of motion is in this way. So t is increasing, right? So because this is time, so the motion is in this way. And so in the phase diagram, we need to put the direction of motion is away from the origin. And in this case, so below the t-axis, the motion will be, so t is increasing, t is time, so the direction will be in this way. It will be toward the origin. well. Now, so maybe we may discuss this later in just a moment. I want to discuss the following. So the advantages of phase portraits is that it is less dimensional than for integral curves, right? And sometimes it may happen that for different differential equations we have the same phase portraits, right? But the speeds of motion along these phase trajectories may be different. So this was example number 1, and let's consider example number 2. Let's consider differential equation of the form x prime equals the absolute value of x. So in this case, we have an equilibrium point x, which is identically 0. If x is greater than 0, we are trying to solve this, and the solution will be, so dx over x. So I know the solution may be, so this is linear differential equation with constant coefficient, so it is x equals c times e to the power t. If x is less than 0, we have the following, and x is equal to c t to the power minus t. Then the integral curves are the following. So this is t, this is x. We have so the constant function, and it is projected into the origin. And c times e to t will give us these trajectories. Not with vertical asymptotes as before. So c e to t is different from this equation, right? These equations are different, and there is no vertical asymptotes here. But now, in this case, we have c e to negative t. Okay. So c is positive. C may be positive or negative. Right? It will be something like this. Okay, so this is for x, which is positive, and for negative, sorry, for negative is not. So this is for negative. For negative, we have not this, but so c. So c is positive here, and c is negative here. For negative c, it will look like something like this. Okay. Okay, so integral curves are different. Integral curves are different because we have two different functions. This one and this. But if we speak about phase portraits, then we speak about the projections. So the projections are the same. Look at the phase portraits, they're the same. So phase portraits may give some qualitative, maybe qualitative picture of our differential equation, but sometimes so phase portraits do not include the speed of motion along these orbits. So integral curves may be different, but phase diagrams are the same. Well, so the phase portraits will not give us a complete information about the differential equations. So if we compare these two cases, right, so different differential equations, different integral curves, different speeds along integral curves, but the phase diagrams are the same. Well, after this we will, so from now on to the end of our lecture and our seminar, we will speak about planar linear systems. And we need to obtain different qualitative patterns, geometric patterns of linear differential, two-dimensional differential equations. In what follows today, we will consider planar linear systems. X prime equals AX, where X is two-dimensional. We will consider phase portraits and different geometric patterns for phase portraits for this linear system. First of all, I will prove the following theorem. Theorem number 2. So the planar linear system equals AX has a unique equilibrium point if unique equilibrium point, which one? So X, which is identically 0. Because so this function satisfies this differential equation. So if we differentiate a 0 function, we will get 0. And if we multiply the matrix by 0 vector, we will get 0. So this solution satisfies this equation, and it is an equilibrium point in accordance with the given definition. Right, so this is an equilibrium point. So if and only if the matrix A is invertible or non-degenerate, so a straight line of equilibrium points if and only if the determinant of A is 0, but A is not identically 0. It's not a 0 matrix. Okay, so proof is straightforward. So for the first point, a unique equilibrium point. So we know that by definition, x0 is an equilibrium point if and only if it is a root, it is a solution of the equation equals 0, right? So this is by definition. X is a critical point or an equilibrium point if by definition it satisfies this equation. But if the matrix is non-degenerate, then this equation has only trivial solution. Okay. If the determinant of the matrix A is 0, but matrix A is not 0, so I will let it A be the following matrix: A, B, C, D. Then we are trying to solve the following: A times x1, x2 equals 0, 0, which is the same as ax1 plus bx2 equals 0, cx1 plus dx2 equals 0. And these two equations, since A is not a zero matrix, then at least one of the coefficient is not 0. But since the determinant of A is 0, then these two equations are proportional, and the solution of this linear system will give us a straight line, and we will get a straight line of equilibrium points. But now we will be interested in the first case when A is non-degenerate. And we will try to classify phase diagram according to geometrical pattern, according to so the nature of eigenvalues of the matrix A. So I'd like to recall that if we are trying to solve how to solve this linear system. So we need to write the characteristic equation, find the roots of the characteristic equations. They are eigenvalues of the matrix A. Then the next step is to find the eigenvectors and write down the answer. Right? This is the plan for solving equations of this form. Well, suppose we have completed the first step. Given the matrix A, we get, so let it be A, B, C, D. Then step number 1 is to solve the characteristic equation. And from which we obtain two eigenvalues. They may be identical or they may be different, so the repeated root or two different roots or complex roots may be. And depending on the nature of these eigenvalues, we will try to classify phase diagrams. And the first case was, so it will be here. So the first case number 1. So suppose lambda 1 and lambda 2 are real, have the same signs, so different, real different, and have signs, the same signs. So we will start with the case when lambda 1 and lambda 2 are both negative. Okay, and satisfy this inequality. Lambda 1 is less than lambda 2, less than 0. we're trying to analyze the phase portrait, the solutions of the differential equation and the phase portrait. So we know that in this case, the general solution can be written in the form C1 times e to the power lambda 1 t times V1, which is the eigenvector, plus C2 e to the power lambda 2 t times V2, where V1 and V2 are corresponding eigenvalues. So V1 associated to and V2 is associated to lambda 2. Well, let's try to analyze this equation, this solution. So our phase diagram will be two-dimensional, right? Two-dimensional. And first of all, so I will start to draw the phase diagram, and I will start, so maybe I will use this space, right? This is the origin. And the determinant of matrix A is non-zero, so we have a unique equilibrium point, the origin. This is the origin. I don't want to indicate the axis because so since this may be confused with the phase trajectories, right? So I will not indicate the axis. I will indicate only the vectors, so the lines through the vectors V1 and V2. So suppose this line is determined by V1, this line is through V1, and this line will be through V2. These are not axes, but these are lines determined by eigenvectors. And I don't want to indicate the directions of these vectors like this, because we can confuse this with the direction of the phase trajectories, right? So only lines. We start with the lines. Through the vectors V1 and V2. So we have a vector V1 and draw a line through V1. This is the equilibrium point. So if we start from this point, we will remain at this point for any t, right? We will not go away. So if x is 0, then x will be 0 for any time, right? So we will not go away from this point. Since so lambda 1 and lambda 2 are negative, look at this solution. We can see that the vectors are multiplied by some, so C1 and C2 are fixed, suppose they are fixed, and we consider one phase trajectory, so fix C1 and C2. If t approaches positive infinity, then we can see that x approaches what? So look at the formulas. V1 and C1 are fixed, C2 and V2 are fixed, but this coefficient approaches 0 as t approaches positive infinity, right? So lambda 1 and lambda 2 are both negative. So these coefficients approach 0. This means that x approaches 0, right? So if we start from some point, the trajectory must go toward the origin, right? Toward the origin. The direction will be this, right? Next, go further. So if t approaches negative infinity, then x approaches positive infinity. So in this case, if so if we reverse the time, x will go away from the origin, Next, if our trajectory starts at the line through the vector v1, let's analyze trajectories that start at a point on the straight line through v1. What does this mean? So if we take the point here, then this means that C2 is 0. Okay, so if C2 is 0, we have a solution of the form P1 times e to the power lambda 1t times V1. And we can see that for any value of t, we get the vector which is proportional to V1, So V1 is multiplied by some coefficient that approaches 0 as t approaches infinity, right? So V1 multiplied by some coefficient. This means that if we start with a point at the line through V1, we will remain on this line, and we will go toward the origin. So the motion will be toward the origin in this way. If we start from this point, we will also go to the origin. If we start, what will happen if we start at some point on the line through V2? Also we will remain on this line, because this means that C1 equals 0 and x will be C2 times e to the power lambda 2t times V2. We will remain on this line, so the motion will be toward the origin, staying on this line, right? So I will remove this point. So so this is the motion on the lines through the vectors. Next, if we start with a point which is outside of the both lines, what will happen? Let's analyze this situation. So I will use that part of the board. All right, are both non-zero, but I want to predict the behavior of this phase diagram. So it may go in such a way, right? But what happens with a trajectory? I want to know the qualitative pattern, right, of this trajectory. Right. So x, I will rewrite this in the following form: e to the power lambda 2t will be multiplied by c1 times e to the power lambda 1 minus lambda 2 times t times the vector v1 plus c2v2. We remember that both c1 and c2 are non-zero, right? So this component is non-zero. Let's look at this coefficient. What happens with this coefficient as t approaches positive infinity? Lambda 1, so by assumption, lambda 1 is less than lambda 2. Then lambda 1 minus lambda 2 is negative, right? It is negative. So this coefficient will approach 0. will approach 0. And so this term will approach 0, and we will approach the line through the vector v2, right? As t approaches positive infinity, our trajectory will go toward the origin, but it will tend to the line through v2. So it will become closer and closer to v2, right? So this term will approach 0, and we will approach the line through v2. So the behavior will be like this. So we can see that all the trajectories will be tangent to the straight line through v2. And symmetrically, we have this. All the lines except for all the phase trajectories will be tangent to the line through v2, except for the trajectories starting at the points on the line through v1, right? All other trajectories will be tangent to this this straight line, and this type of phase diagram is called a node or a nodal sink. This is a nodal sink because all the trajectories move toward the origin. It is nodal sink. The type is called a nodal sink. Okay, so if lambda 1 is greater than lambda 2 greater than 0, then the form of phase trajectories will be the same, but the direction of motion will be reversed, right? Because so the formula will be the same. The qualitative analysis of this formula will be the same, but we should reverse in these directions. X approaches positive infinity must be switched with this situation. If we switch them, we will obtain the qualitative pattern for this case when the eigenvalues are both positive and non-equal. So the figure will look like this, but the motion will be away from the origin. And this is called a nodal source. A nodal source. A nodal sink versus nodal source. Well, so this is the first type, and now we will consider an example. So today I decide to construct my lecture in the following way. So I will consider some case, some type of phase diagram, and I will give an example or maybe several examples, and this will be done during the lecture, and it will be continued during the seminar, right? Because the seminar is the same as the lecture, right? So a type and an example, and after this you will try to do the same at home. right? So now let's consider a task from this seminar. Okay, task 1 will be, so for each of the systems, in the following problems, so you should do the following: find the eigenvalues and eigenvectors, classify the critical point as to type, the critical point 0, 0, so the origin as to type, sketch by hand without using any graphing device several trajectories in the phase plane. And the last task will be use an appropriate graphing device to plot accurately several trajectories. So it will be interesting. So first try to do this by hand without graphical device, and then to see this on the screen of the computer, right? It would be interesting. So now we can't use the graphical device. Maybe we can ask you to help, but I think not. Something like Wolfram alpha can be considered. Right, so task number 1, x prime equals 2x, y prime equals x plus y. So this is an example of a linear system. Let's try to find eigenvectors and eigenvalues first. So the first step is to write down the matrix A. It is 2, 0, 1, 1. Then characteristic equation. So we need not do this. The answer is clear. Lambda minus. Sorry? I can't catch. I can't catch what is. Can you write in the chat? Can you write in the chat, please? Okay, so the answer is lambda equals 1 and lambda equals 2. So these are roots. They are different. They are both positive. So we have the following: 0, 1, and 2. So what is the type of the phase diagram? Can you answer? What is the type of the phase diagram in this case? So these are two eigenvalues. They are both positive and different. Nodal thoughts, yes. Well, but next we want to have a qualitative figure, right? So to do this, we need to know the eigenvectors. Let's find them. Eigenvector associated to this eigenvalue. So we need to solve the following. From which it is clear that as the vector v1, we can take 0, 1 is the vector v1. And for lambda 2, which is equal to 2, we have the following: 0, 0, 1, negative 1. And so for the vector v2, we can take 1, 1. Now draw the figure. So these are axes, but the line determined by this vector will be 0, 1. So it is this vertical line. This line corresponds to the vector v1, so without any direction, right? And 1, 1 is this straight line. Okay, so this is an equilibrium point. So now, since it is a nodal source, then the direction is away from the origin. And after this, we must decide which vector to approach, right? v1 on v2 or v2. So x is equal to c1 e to the power t 0, 1 plus c2 e to the power 2t 1, 1. If we represent it as e to the power 2t multiplied by c2 1, 1 plus c1 e to the power negative t so I think it's better to let it be in two ways. So as t approaches as t approaches positive infinity, that if we start from this point, maybe the behavior of this will be like, it will tend to the line through 1, 1, but as t approaches positive infinity, so in this way. But as t approaches negative infinity, so we are interested in the behavior near infinity, so the behavior near 0, right? So we need to know the behavior of this trajectory as t approaches negative infinity, and so we should do the following: e to t times c1 0, 1 plus c2 e to t 1, 1. As t approaches negative infinity, we are close to 0, and near 0, so this approaches, if t approaches negative infinity, this approaches 0, and we approach to this vector. So we need to approach the vertical line. So it must be tangent to the vertical line in this way. So after finding these eigenvectors, we need to determine which line to which line our so which line will be the tangent line for our trajectories, right? This straight line or this of the vertical straight line. It depends on the inequality, right? On whether lambda 1 is greater lambda 2 or less than lambda 2. So in our case, our trajectories are tangent to the vertical line, so we're trying to draw this. And if you use some computer devices, you will be programming devices, you will be able to check yourself, right? In this way. something like this.
And t approaches negative infinity, even for t approaches 0,
right? So because first I started with this, right? But this will not give us the structure of the phase diagram near the origin, because we need to know the behavior near the origin. If we want the behavior near the origin, we should consider the case when, in this case, we need to consider t approaches negative infinity, right? And so I will change my choice to this. So this is not correct. So this is correct, of course, but as t approaches positive infinity. So if we far from the origin, then our phase trajectories resemble that. So this, for example, so they become almost parallel to this straight line. Actually, the figure like this, but near the origin, this direction is more important, right? This term is dominant, and this term is negligible small in comparison with this first term, right? So this is the dominant term as t approaches negative infinity. So this is the way for analyzing the behavior of phase trajectories. Well, let's go further. Now we will move on to case number 2. Real eigenvalues of opposite signs. So I will use that part of the board. So case 2. Let's have a look. Okay, so real suppose lambda 1 is less than 0, less than lambda 2, or vice versa. Let's analyze this. So the formula for the solution is the same. And we must start with the vectors, the directions determined by v1 and v2. This is the origin. It is the equilibrium point. Well, let's analyze first the line through v1, for example. Let's consider the line through v1. So lambda 1 is negative. So in this case, we have c2 equals 0 if we start on v1. Then c2 is 0, and the solution has the form c1 e to the power lambda 1 t v1. Since lambda 1 is negative, then as t approaches positive infinity, x approaches 0. So we go toward the origin. So the direction is toward the origin. But what about the line through v2? So then this term is 0, and lambda 2 is greater than 0. So as t approaches, so if c1 equals 0, then x equals c2 e to lambda 2 t v2. And as t approaches positive infinity, x approaches positive infinity, right? This means that we move away from the origin. Something like this. Okay. And if we start at some point here, for example, or here, what will happen? then. Okay. So if we consider this equation, then as, for example, t approaches positive infinity, then this term will approach 0, and x will approach, so if c1, for example, is not 0 and c2 is not 0, then as t approaches positive infinity, this term will approach 0, and this term will approach the line through V2 asymptotically, right? So this is the line through V2. This means that it will be something like this. So the asymptotic behavior, so it will be the behavior like this. With direction, of course. The direction will be the direction will be away from the origin, right? Because if t approaches positive infinity, this approach 0 and this approach infinity, positive infinity, right? But close to the line through V2. So all the trajectories will asymptotically approach this straight line through V2. So this will be the direction. And this is called a saddle point, saddle. So it's time for a break. Now let's have a break for 10 minutes, and after this we will continue. So we will consider an example for this case and move further.